Hello and welcome to your second recording for this week. Just a reminder, I am still out testing for makeup OGTs. I will be out Monday and Tuesday, and we will resume live classes at the normal time, 9:15 a.m. on Wednesday. Today we will be continuing Unit 3, Lesson 2, working with arc and angle measures in circles. As you saw in the first recording, here are the learning objectives for the week. We started identifying and finding angle measures of arcs. We are going to continue that in this recording as well. And then the next couple of recordings we're going to use inscribed angle to solve problems and use angles on and inside circles to solve problems. So we are going to pick up right where we left off. This next important idea is that congruent chords have congruent minor arcs. So when we talk about chords, if you think back to last week, we talk about chords. Chords are segments that have endpoint on the circle itself. So here we have chord DB, and here we have chord AC. So in the same circle, or in congruent circles, congruent chords have congruent minor arcs. So what this essentially means is that if you are told that DB is congruent to AC, then we can conclude that arc DB, which refers to this arc here, would be then congruent to arc AC. And so here I'm going to show you guys a quick proof of this. So in the following diagrams, I tell you that arc DB is congruent to arc AC. And so from there, I've constructed triangle DOB and AOC using the radii, DO, BO, OA, and OC. And because these are all radii of the circle, they're all the same length. So I'll just give each of those 2 tick marks. So now we can use congruent triangles to say that triangle AOC, this bottom triangle here, is congruent to BOD, this top triangle, using the side, side, side postulate. So because these 2 triangles are congruent, we can then say that all remaining pairs of corresponding parts are congruent, such as this angle here, DOB, and this angle here, AOC. And so that is just using corresponding parts of congruent triangles are congruent. We get that those 2 central angles are congruent. And then that leads us to the conclusion that, as we learned last time, that congruent central angles have congruent arc measures. So because arc AC subtends angle AOC and arc DB subtends angle DOB, these 2 arcs are congruent. Okay, so again, all congruent chords in the same circle or in congruent circles have congruent minor arcs. Let's look at our next main idea. Here we are told that congruent minor arcs have congruent chords and congruent central angles. This kind of combines all of the ideas so far. So in the same circle or congruent circles, congruent chords, so for example, if we look at chord DB and chord AC, if these chords are given to us as being congruent, or sorry, let me take that back. Let's start with the, we want to show that these chords are congruent. So let's start with this diagram here in which arc AC is congruent to arc DB. So this time I'm going to start with the arc measures. So let me highlight those in, we'll do green. Arc DB and arc AC. I'm going to say that those are congruent to start with. So let's put on a mark on each of those. So if that's the case, in our diagram we can see the radii again that we've used. DO, OB, OA and OC. Those are all congruent because they start at the center and go to the outer edge of the circle. Those are all radii. And since we know that arc AC in green is congruent to arc DB in green, that means the corresponding central angles are congruent, or this angle here and this angle here. And again, that is using the idea that the central angles subtend the two congruent arcs that we are given. Or we could even say that these are actually a pair of vertical angles because they're formed by two intersecting lines with angles opposite each other. And so now we can actually use the idea of these triangles, the top and the bottom, to say that since these are radii, these are congruent to each other. And so we have side, angle, side to show that these two triangles are congruent by the side, angle, side postulate. And then because of that, we can then conclude that all remaining pairs of corresponding parts are congruent, meaning chord DB and chord AC. So that will be these two here, chord DB and chord AC. So we can use congruent triangles to show different relationships between arcs, central angle measures, and chords inside circles. So let me summarize the properties that we've talked about so far. So our first theorem says that congruent central angles have congruent chords. So if I'm told that I have two congruent central angles, angle DAE and angle CAB, you can see that they're given as congruent with these arc marks. If I know that these central angles are congruent, then I can say that their chords, or the segments drawn in between their endpoints, are also congruent. And so that would be DE is congruent to BC. That would be this chord here and this chord here. So that's the first one. The second one that we looked at says that congruent chords have congruent arcs. So if I start with congruent chords DE and CB, or ED and BC, then I can then conclude that the arc subtending those chords, or the part of the circle that is between and including those endpoints, so arc DE and arc BC, are also congruent. And then the last one says that congruent arcs have congruent central angles. So if you are told this time arc DE is congruent to arc CB, or arc ED is congruent to arc BC, remember you can switch the letters around and it refers to the same arc, then you can make the conclusion that if you have those arcs congruent, then the central angles subtending those arcs are also congruent, meaning DAE and BAC. And so now let's do a couple of problems where we practice using these properties. So here we have example 1. We want to find the measure of each of our arcs. So what it's easiest to do is just to kind of fill in information as we go. And as we fill in missing measures, I'll explain to you guys why each of those are congruent. So if we look at this diagram here, I'm given that this central angle MOL is 60 degrees. Notice that if I extend this part of the angle all the way across the other side of the circle, and I do the same with this one, we have a congruent angle pair up here by vertical angles. So this angle is also 60. Okay, so the next thing I can do is realize that these lines here are diameters of the circle. So they open up to a semicircle, which is exactly half of the amount of degrees in a circle. So if I just was looking for this green angle measure here, I can just give that 2 lines. To find that, I can just take 180, and I can subtract off the 60 degrees. that I know from this angle here. And that will give me that this angle in green is equal to 120 degrees. Now you might say, why do I care about this? They're only asking for arc measures. Well, we can know a lot about circles when we find angle measures and then look at the arcs subtending each of those central angle measures. That'll give us an idea of the arcs corresponding around the outside of the circle. So again, using the vertical angles theorem, if I extend these green lines, then I know this angle here is also 120 degrees. And then the theorem that we talked about, central angle measures have congruent corresponding arc measures. So that helps us out quite a bit. I can say that the part of the circle from M to L here has the same measure as its corresponding central angle measure. So in that case, I can say that the measure of arc ML is also 60 degrees. And that is true also for the arc of PO over here. So I could put 60 on the outside referring to this arc. Now the next part is asking us to find PM. So that's the part of the circle that goes between point P and point M, so this outside here. And so that has the same measure as the central angle that it corresponds to, so that is also 120 degrees. And now finally they're asking me to find, I'm going to try to use a different color here, I'll just use black. They're asking me to find the measure of arc LMQ. This is a major arc here because it has 3 letters. So if I start at L, I move around the circle to M, and then all the way around to Q, which looks like it's all the way around to here. That's a Q there. Then I just have to add up those arcs using the arc addition postulate. So I could say that the measure of arc LMQ is equal to the measure of arc ML plus the measure of arc MP plus the measure of arc PQ. And so that gives me 60 plus 120 plus 60, which will give me 240 degrees. All right, let's try one more set of problems. In this example, we are given circle O, so that's named by the center here, and we want to find the measure of arc AB. Now notice I have 3 big arcs going around this circle. I have AB, I have AC, and I have BC. And these 3 arcs make a full circle. So I know in a full circle there are 360 degrees. So all I need to do is take each of these expressions, add them all up, and set them equal to 360. So I have 3x plus 15 plus x plus 20 plus 4x plus 5. And all of that has to equal 360 degrees because there are 360 degrees in a full circle. So combining like terms, 3x plus 1x is 4x, plus 4x is 8x. And then I have 15 plus 20 is 35, plus 5 is 40. That equals 360. So solving this, I just take away 40 from both sides. And that leaves me with 8x is equal to 320. And my last step is to divide by 8. So x is going to equal 40 degrees. Now I want to find the measure of just arc AB, so I plug it in here. And 40 plus 20 is going to give me 60 total degrees. So the measure of arc AB is equal to 40 plus 20, or